In the world of software development, we often encounter similar problems. Design patterns offer elegant solutions to these recurring challenges. They provide proven blueprints for structuring our code, making it more efficient, reusable, and maintainable. Think of them as time-tested recipes for building better software. Design patterns are not language-specific. They are conceptual solutions that can be implemented in various programming languages, including Python. By understanding and applying these patterns, we can write cleaner, more organized code. This leads to more robust and scalable applications. Design patterns encourage best practices and improve communication among developers. They provide a common vocabulary for discussing and solving design problems. This is essential for building high-quality software, especially in collaborative environments. One of the key principles in software engineering is don't repeat yourself dry. This principle emphasizes the importance of writing reusable code. Design patterns, including the factory pattern, embody this principle. They promote modularity and flexibility in software design. The factory pattern, in particular, addresses a common problem, creating objects without specifying the exact class of object that will be created. This pattern provides a centralized place for object creation, making our code more adaptable to change. By abstracting the object creation process, we decouple our code from concrete implementations. This means that we can easily add new product types or modify existing ones without affecting the rest of our code base. The factory pattern is a creational design pattern that provides an interface for creating objects. However, it lets subclasses decide which class to instantiate. In simpler terms, we define a separate class, the factory, whose sole purpose is to create and return instances of other classes. This pattern promotes loose coupling between objects by delegating the responsibility of object creation to a specialized factory class. Instead of directly instantiating objects using constructors, we ask the factory to provide us with the objects we need. This approach offers several advantages, including improved code organization, reduced code duplication, and increased flexibility in object creation. We'll explore these benefits in more detail later. Encapsulation is a fundamental concept in object-oriented programming, OOP. It refers to the bundling of data and methods that operate on that data within a single unit, the object. The factory pattern leverages encapsulation by hiding the complexities of object creation within the factory class. The client code interacts with the factory through a well-defined interface. It doesn't need to know the internal details of how objects are created or which concrete classes are being instantiated. This abstraction simplifies the client code and reduces dependencies between different parts of the application. By encapsulating the object creation logic within the factory, we make our code more maintainable and less prone to errors. If the creation process for a particular object type changes, we only need to modify the factory class, not the client code that uses it. Section 5, Step 1, defining the blueprint or interface. To implement the factory pattern in Python, we'll start by defining an interface or abstract class that represents the common behavior of all the objects we want to create. This interface acts as a blueprint for our concrete product classes. Python from ABC import ABC, abstract method class vehicle ABC, at abstract method def start self, pass at abstract method def stop self, pass. In this example, we define an abstract base class called. It has two abstract methods and which must be implemented by any concrete class that inherits from. This interface ensures that all our vehicle objects will have a consistent way of starting and stopping, even though the implementation details might differ. Section 6, Step 2, creating concrete products. Next, we create concrete classes that implement the interface. These classes represent the actual products or vehicles that our factory will create. Python class car vehicle, class bike vehicle. We define two concrete classes and both inheriting from the interface. Each class provides its own implementation for the and methods reflecting the specific behavior of that vehicle type. Now we have concrete representations of our vehicles, each adhering to the common interface defined earlier. Section 7, Step 3, the factory in action. Finally, we create the factory class itself. This class will be responsible for instantiating and returning the appropriate vehicle object based on the input provided. Python class, VehicleFactory, def create, vehicle, self, vehicle underscore type. If vehicle underscore type equal sign car return car, elif vehicle underscore type equal sign bike return bike, else raise value error invalid vehicle type. The class has a single method. This method takes a string as input and returns an instance of the corresponding concrete class. If an invalid vehicle type is provided, it raises A. Now we have a centralized factory that handles the creation of our vehicle objects. Section 8, real-world analogy, the vehicle factory. Imagine a vehicle manufacturing plant. It's a bustling place filled with activity and precision. This plant produces various types of vehicles such as cars, bikes and trucks. Each type of vehicle has its own dedicated assembly line. The factory has different assembly lines for each vehicle type, but they all share a common entrance where raw materials arrive. These materials are then sorted and directed to the appropriate assembly line. The factory pattern in software development is analogous to this vehicle factory. It helps in creating objects without specifying the exact class of object that will be created. The factory class represents the manufacturing plant, while the concrete product classes, car, bike, truck, represent the different vehicle types. Each class has its own unique characteristics and methods. The client code is like the customer who places an order for a specific vehicle type. They specify what they need without worrying about the details of how it will be made. The factory takes care of routing the order to the appropriate assembly line or concrete class and delivers the finished product or object to the customer, which is the client code. This ensures efficiency and consistency in production. The customer doesn't need to know the intricacies of the manufacturing process. They just receive the vehicle they ordered. This abstraction simplifies the interaction and enhances user experience. Section 9, benefits of the factory pattern. The factory pattern offers several benefits, making it a valuable tool in software design and development. First, modularity. It promotes a clear separation of concerns by isolating the object creation logic within the factory class, which is crucial for maintaining clean architecture. This makes our code more organized and easier to understand, reducing the cognitive load on developers. Next, flexibility. It allows us to introduce new product types or modify existing ones without affecting the client code, thus enhancing the adaptability of the software. We only need to update the factory class, ensuring minimal impact on other parts of the application, which streamlines the development process. Lastly, maintainability. It simplifies code maintenance by centralizing the object creation process, making it easier to manage and update. If a change is required in how an object is created, we only need to modify the factory class, not every instance where that object is created, saving time and effort. By adhering to these principles, the factory pattern contributes to more robust, adaptable and maintainable software, ultimately leading to more successful projects. Section 10. When to use the factory pattern. The factory pattern is particularly useful in the following scenarios. First, when we need to create objects but don't know the exact class of object that will be created until runtime. This could be because the choice of class depends on user input, configuration settings, or other dynamic factors. Next, when we want to encapsulate the object creation logic and hide it from the client code. This simplifies the client code and makes it easier to maintain. By centralizing the creation logic, we reduce redundancy and potential errors. Lastly, when we want to introduce new product types in the future without modifying the existing client code. The factory pattern makes it easy to add new concrete classes to our application without breaking existing functionality. This ensures that our code base remains flexible and adaptable to future changes. By recognizing these situations, we can effectively leverage the factory pattern to improve our software design. This pattern not only enhances code maintainability, but also promotes scalability and robustness in our applications. Section 11. Conclusion. The factory pattern is a powerful tool for writing flexible and maintainable object-oriented code. It provides a way to encapsulate the object creation process, decouple our code from concrete implementations, and make it easier to add new product types in the future. By understanding the principles behind the factory pattern and applying it appropriately, we can write cleaner, more organized, and more adaptable software. This pattern, like other design patterns, empowers us to build better software by leveraging proven solutions to common design problems.